Welcome back, everybody. Thank you guys so much for taking the time to come down and sit down. We are going to be starting with Eric Jordan's next presentation. He will be presenting on the art of software engineering. Eric is a wonderful guest that we have today. He's also the professor of our capstone class here at UMBC. So, believe it or not, Eric has done a lot of things with the club over the years. So we're really grateful to have him here today. And take it away.
Hi. I'll spend a minute introducing myself, but not too much time. I founded the UMBC Game Developers Club 21 years ago. For anyone my age, the time really goes by very quickly. It seems like only yesterday I was in this same lecture hall hosting the very first DEC. Since then, I've spent well over a decade in the game industry. A lot of that time at Firaxis Games, working on games like Civilization V, Civilization VI, XCOM Enemy Unknown, and Marvel Midnight Suns. I also spent a little bit of time at Breakaway and Oxide, and currently I'm at Meta. I've been at Meta for a little over 5 years now. Worked a lot with the VR gaming there, and currently doing some of the integration between AI tools and games right now. So that all out of the way, let's get started on the talk. Now, I know some of you might be thinking, oh no, I'm not a software engineer and this is going to be a very boring talk. I have some good news for you. This is a very accessible talk. It's really more about principles of engineering and how they apply to software. And it's something that anyone can understand, even if they've never programmed a line of code in their life. I also think what's kind of interesting about this talk, I've given it before, and I was wondering, how relevant is this going to be? Things in software engineering are changing very quickly. AI-generated code is playing a greater and greater role, and I was like, oh man, how relevant is my talk still? I went through the slides and actually found it's very relevant still. Because regardless of how much of the code is written by AI or human, engineering decisions are still important, and they still need to be driven by a human. So I'm very excited to share this with you, and let's get started. So we're going to start off by talking about cars. This is the Bugatti Chiron, and we're going to ask ourselves if this is a well-engineered car. So let's look at some of its stats. It has 1,479 horsepower, a top speed of 261 miles per hour. That's electronically limited. It might even be able to go faster. Wow. So is this good engineering? Well, it depends where you're driving it. If you took this Bugatti Chiron out to this desert, it wouldn't go very fast. But this Jeep would probably overtake it. So what does this tell us? It tells us that context is incredibly important when making engineering decisions. As cool as something looks, it's not going to be effective if it's used in the wrong context. One of the books that for me was most influential for me growing as a software engineer was a book that was not supposed to be very influential. It was a reference manual for the standard template library in C++. And it was just kind of going through all the various different collection types and the places where you would use them, where they were strong fits and where using them might be problematic. And this was, for me, as a very young engineer, when it started to dawn on me just how important context is and how important it is to match your solution with the context. Engineering is all about trade-offs. When they went about designing that Bugatti Chiron, there were some specific goals they had in mind. Affordability was not one of them. Reliability was not one of them. Safety was not one of them. Weather was not one of them. They wanted a car that would go really, 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 really fast and still be street legal. So whenever you're, choosing your solutions, there are going to be trade-offs, right? Like you might have a collection type in programming that is really good at, inserting new elements randomly in different places, but is not so good at linearly going through those elements, right? So it's really important to think about, not just is this a cool, good thing, but, what trade-offs are being made here, and do they fit with our goals? Context is essential when approaching any engineering problem, and we use that context to choose what trade-offs to make. And finally, it is near impossible to judge the value of a design without knowing the context it will be used in. All right, so we're armed with, okay, yeah, so I said, some designs are bad no matter what the context is true, but for the most part, to choose, the right design, we need to know about our context. So I'm gonna start with some context here. So here's our context. We've got smooth road, we've got good weather, we've got a race driver who can handle a lot of power, and speed is an important design goal. All right, armed with all that, now we have a choice. We could get the Bugatti Chiron, or we could get this Reliant Robin, and it has 3 wheels. It looks a lot slower. So we might feel pretty confident in our answer now, that obviously this Bugatti Chiron fits this context better. Well, we decided to go that route, and we started building a Bugatti Chiron. And we only got this far. We completed the engine, but then we ran out of time and money. And this poor woman, she's pushing this as fast as she can, but it's not going very fast. And the Reliant Robin will beat this around the track. So, what does this tell us? Context isn't just about the context the product will be used in. It's also the context of development. How much time do we have? How much budget do we have? Years ago, I was here, this was maybe like 10 years ago or something, it was a while ago. I was here judging a game jam competition. And there are a number of teams. One of the teams was some high schoolers. Most of the teams were college students. And one team was some professional developers. And the professional developers were not able to finish their project. And everyone else did, even the high schoolers did. Because the professional developers sat down and they're like, well, we're going to start engineering things and building them like we would at work. And they weren't properly adjusting for the context of being in a game jam when they only had 2 days. So it's really important to adapt to whatever environment you're in, and understand that the choices you make in a new environment might not be the same choices you make in an environment you're used to. All right, so we've learned a lot. And now, surely, this next choice will be easy for us. Which is better, JavaScript or C++? The answer is C++, but the truth is, you don't really know without knowing the context. But as I demonstrated, a lot of engineers will very quickly answer this question. And so why is that? Even though we know that we need context, why is it that engineers will have a very fast answer to this question? And it won't always be the same. Well, I would call this like technological prejudice. And what does that mean? It's basically preferences that sometimes make us forget our context. How do we end up with those? Well, there are a lot of things. One is, a lot of times it's just what we're used to using, what we've used in the past, what we're comfortable with, what our friends and colleagues like. That's a huge influence. And, probably related to all of these other things, what's best for the contexts that we're used to working in? As someone who's worked on a lot of big AAA projects, game projects, where performance was an important goal, JavaScript would have been a poor choice, I think. However, working at Meta now, I know and work with a lot of people with more of a web and app development background who think that C++ is too hard and I'm crazy for liking it. So it just, our backgrounds really affect what our preferences are. And I think as an engineer, it's always important to, realize the biases that you're starting with and try to adapt to new circumstances. It's a quote from someone I used to work with who I thought was great. I had a great quote. He said, just because the roof is caving in doesn't mean roofs are a bad idea. This can happen sometimes. Sometimes someone will try a new piece of technology and they'll have a really bad experience with it. And then they'll come away with sort of a decision like, oh, this is always bad, you should never use this. Sometimes it's just that you ran into a poor implementation, or that technology was being used in a context where it didn't fit very well. So let's shift gears a little bit and talk a little bit about dealing with complexity. There's a lot of software engineering. If you're a student, you're probably used to working on projects that are extremely small and you're the only developer. And it takes you, 5 to 10 hours to complete your homework assignment. And you don't really have to worry about, some massive code base with hundreds of thousands of lines of code and, potentially 100 or more engineers contributing to that code. But when you get out into the working world, this is what software engineering is all about, is you have these massive projects and how are you going to keep them organized and not a total disaster. So there are a number of techniques for that. One common thing is design patterns. This is a physical example of a design pattern. This design pattern is called a lever. You see it pop up in all sorts of mechanical engineering. But just like with physical engineering in the real world, software engineering has these design patterns that we follow over and over again. And they can be really helpful. If you have a bunch of design patterns, it can be kind of like a little bag of tricks that you have. Of course, like everything, they can also be applied incorrectly. So design patterns, they're essential tools for engineering. However, they only work if they're applied correctly. So the correct context, a good implementation, and there is no such thing as a panacea. There is no such thing as a solution that's going to work everywhere. So I'm going to give an example of a design pattern going wrong. So this is for inheritance. I guess this is something, this particular slide, you might need more of a comp sci background to understand, but this is a real scenario. So the Australian Air Force is making a VR simulator for helicopter combat training. The programmers want to model the movement of kangaroos and their reactions to helicopters. This is Australia. It's a big problem over there. So they wanted to make, they wanted an easy way of reusing some of the code they had for other creatures moving around on the environment. And the creatures moving around the environment that they had were soldiers. So they made kangaroo a subclass of soldier. And for people who don't have a software engineering background, or even for people who do, it's an important reminder. Inheritance is a relationship. So a good way of knowing if you're going to run into trouble is to just say it in English. Kangaroo is a soldier, and see if there's a problem with that. So, as a result of the kangaroos inheriting from the soldier, during a client demo, the kangaroos scattered in reaction to the helicopter. So that was good, that was correct. Then they reappeared from behind the hill and launched a barrage of Stinger missiles at the helicopter. So to go back to Tim Kipp's quote, I mean, just because the roof is caving in doesn't mean that roofs are a bad idea. This is not to say that inheritance is bad or you should never use inheritance. It's just to say that anytime you apply any design pattern, you need to think carefully about whether or not the design pattern is the correct fit for what you're doing. And this kind of comes back to the idea of, code reuse, which is very important. You don't want to keep writing the same code over and over again. It's inefficient to remake similar systems over and over again. And we can save lots of time and money by reusing code. Not only that, there was a study from long ago that I think was a very influential study in the field of computer science. They studied the relationship between the number of lines of code and the number of bugs. And they found that that relationship was very heavily correlated. And in fact, they found that a lot of other previous research, they could explain the increase in bugs they were seeing simply by the number of lines of code. So a lot of previous research was like, all of a sudden came into question because it was like, well, was it really shifting from paradigm A to paradigm B, or was it just the fact that the number of lines of code was less? So there's another reason why code reuse is super important. And of course, that saved time allows us to build cooler stuff. So where can this go wrong? Lots of car references. You can tell I'm a Top Gear fan. So sometimes when we're trying to make code that's reusable, we try to serve too many masters at once. In this case, this fine English gentleman has made what he calls a toy-boda. It is both a pickup truck and a boat. And as it turns out, it is not a very good pickup truck anymore, and it is also not a very good boat. So when writing reusable code, you shouldn't necessarily be trying to make code that can serve all kinds of different use cases. It's perfectly okay to write code that serves, and probably a good idea, to write code that serves a very specific use case and serves it very well. Also, when making reusable code, there's this concept of having something that's loosely coupled, and that just means as few interdependencies as possible. That makes it easy to sort of move around from one code base to another. It also makes the code less complex. If you have a library for, say, handling a certain compression algorithm, and it's very well self-contained, that makes that code base a lot easier to maintain. It also, these reusable pieces provide an interface for use with other systems, and they perform a specific and well-defined function. There's also, along with this, sort of this concept of abstraction, which is breaking the code into small reusable pieces, but also an important part of abstraction is the implementation details are kind of hidden away behind an interface. This is both a very good thing and sometimes problematic. Why it's very good? There's really only so much context people can load into their brains. It's kind of funny because now we're dealing with LLMs and we're worrying about the context LLMs can can handle all at once. But people's brains can only handle so much context as well. If you have to understand every single detail about every system you work with, it's going to become overwhelming, and you're not going to be able to move very quickly or effectively. So, hiding these details behind an interface can be helpful. It also allows, programmers to specialize, right? So the abstraction principle, of course, don't repeat yourself, same as code reuse, and makes building and maintaining each piece a little simpler, and allows programmers to focus on a small piece of the software and specialize. So here's an example. I always like to give an example of things going wrong. It's fun for me. But Anne is a physics nerd and has written a physics system for the game. Jim is confused by physics, but is able to use Anne's physics system for the gameplay code. So far, so good. And this is, a good use of abstraction and code reuse. Here's another example. Actually, we haven't gone to the bad example yet. That's good. Alice needs the game to open a compressed file, but doesn't have time to write a decompression code. She downloads an open source library and adds it to the code base. It's a great idea as long as the license is appropriate for your use case. Another example of code reuse and abstraction, Steve wants to make a game quickly and easily, uses Unity. And game engines are really a package of many systems whose implementation details are kind of hidden behind these interfaces. All right, so here's the example of things going wrong. Favorite part. Sometimes you actually do need to know about the implementation. Abstraction can be obfuscation, and unexpected behaviors can occur. So Jim is using Ann's physics system. He applies force to an object in the game. He has forgotten to give the object mass, and its mass has been defaulted to 0. The game crashes with a divide by 0 error, and Jim is flummoxed because he doesn't know how the internals of the system work. I mean, this happens all the time. I don't know if there's really anything we can do to prevent this. You know, it's just sort of the nature of working with these large and complex code bases. I think when people are working in the same code base for a long time, you know, they work at a company and they've been working for that company maybe for 4 or 5 years and it's been the same code base the whole time. They start, their understanding of the system starts to sort of trickle down into you know, various pieces of the code. You know, maybe Jim has this experience. And then, you know, it's really hard to debug it. He needs Ann's help, and they eventually figure it out. But after that, Jim knows something about the physics system. And the next time this comes up, he's like, oh man, don't let your mass be 0. I mean, hopefully it doesn't crash with divide by 0. Hopefully it handles it a little bit more elegantly than that, but these things can happen. All right, so getting bored? Don't worry, it's about to get way more exciting because we're about to talk about Euclid. I know. This is going to be really cool. All right, so who is Euclid? He was a badass. He's a Greek mathematician, mid-4th century to mid-3rd century BCE. He's the father of geometry. He revolutionized mathematical proofs. So this is going to be exciting. All right, so let's talk about Euclid's postulates a little bit. Euclid's postulates are, number 1, a straight line segment can be drawn joining any 2 points. Any straight line segment can be extended indefinitely in a straight line. Given any straight line segment, a circle can be drawn. Well, hold on. Why are we talking about this? There's actually a good reason. When I saw these, I was blown away. When I first saw these, I was already a software engineer with a good number of years of experience. And I looked at what he wrote and I was like, this guy is like the greatest genius who's ever lived. Because postulates are assumptions. He's saying that these things are assumptions. So he's saying all right angles are congruent is an assumption. I thought that was just so brilliant and so cool. And this was sort of how he formed the foundation for his logical proofs for geometry. And it might seem so obvious to us that, of course, all right angles are congruent. You know, of course, parallel lines are never going to intersect. But as it so happened, many, many years later, centuries later, when astronomers were dealing with things in the cosmic scale, you know, things moving close to the speed of light, they were like, oh, space might not be Euclidean at this scale. And because Euclid had put all of these down as postulates, as assumptions, they were able to figure out which proofs still held true and which didn't. So how does this apply to software engineering? Well, you see, all bugs are about false assumptions. So the fact that he was so capable of understanding things that seem so obviously true as assumptions, it just an incredible superpower for software engineers. So here's the most important thing to remember. Bugs comes from defects in the mind of the programmer. It's humbling to think about, but it's true. Start with this. These defects are false assumptions. If a bug seems impossible, then explain why you think it couldn't possibly occur. This is like Euclid putting out his postulates. Listing out your assumptions is the same process that Euclid went through when he created his postulates. After you've listed all your assumptions, test them one by one. When you've tested everything that can go wrong, start testing the stuff that can't go wrong. I love this. When I was at Firaxis at one time, there was a guy who was like a marketing associate. I think he was working on our website. It was many, many years ago. And he had a bug, and he didn't know what to do about it. And he came to me and said, "Eric, I've tested everything that can go wrong." I'm like, "Well, then you better start testing the stuff that can't go wrong." And he came back to me an hour later. It's like, "I found it." So it's true. It's frustrating thing about code, but this is sort of the foundations of debugging. Let's switch gears again and talk a little bit about elegance. This is a Rube Goldberg machine. Rube Goldberg machines are very, very cool. But also, they're not very reliable. They're difficult to make, and they're expensive to put together. Sometimes I think it's easy, even for good software engineers, to accidentally build Rube Goldberg machines. I think it's very easy because we love building stuff, and it's really cool to see everything come together and work. But as I said, a lot can go wrong with a Rube Goldberg machine. This is difficult to maintain. It's inefficient, and more lines of code mean more bugs. So I always strive to make my code as simple as possible. So I will, write out, my change, and then I will go back and try to break it down and simplify it until it looks very simple and obvious. The code I'm most proud of is not the code where it's like, wow, that's amazing. Like, I can't get my head around that. It's code that just seems boring and obvious. And the most exciting thing I think you can do as a software engineer is to take a problem that first seems really, really hard and complex, and then write code for a solution that feels kind of stupid obvious. No one's perfect. I probably haven't in my career always done a perfect job of this, but I think it is a good thing to strive for. And there's a great quote about this. A designer knows he has achieved perfection not when there is nothing left to add, but when there is nothing left to take away. This can be a little frustrating if you work at a workplace that judges engineers' output by lines of code, but hopefully you do not experience too much of that in your career. Another quote I like, I don't know who said this, but find solutions for problems, not problems for solutions. So let's also talk about the shape of the code. This is really important. The first time I gave this talk, there was a pile of water bottles right near the speaker. And it was so convenient. But I'll describe what I did. I was imagining a project where the end goal of the project was to build a tower 2 water bottles tall. And there's a lot of pressure to get to milestone A as quickly as possible. Milestone A was a tower of 1 water bottle high. Kind of makes sense. Kind of like the halfway point of the project, right? So the fastest way to build a tower 1 water bottle high, and I just plopped a single water bottle onto the table. And then I said, okay, great. Now my next milestone is to build a tower 2 water bottles high. And I put a second water bottle on top of the first one, and the whole thing came crashing down. So the point is, early in a software project, when you were laying the foundation, those foundations are really important, and they're hard to change. In the example of the water bottles, I had to throw away my original foundation and make a much sturdier 3-water bottle foundation. And then I was able to successfully get to milestone B with my a water bottle tall tower. So it's really important to focus hard on the foundation and building a solid foundation. If you want to write cheap, hacky code, in the right context, that might make a lot of sense. Just make sure you're doing it at the layer of the shingles and not the layer of the foundation. So as I said, the fastest path from A to B is not necessarily the fastest path from A to B to C. This is also really important. And I think this gets forgotten way too much. More time is spent maintaining code than writing it. This is so important. There is oftentimes a focus on producing code quickly. And I think that's gotten all the more intense recently with AI-generated code. I think it's really important to realize that the biggest expense isn't writing the first version of the code. The biggest expense is maintaining it. Now, there's a little bit of context here. It's a little different if you're doing like a demo or a prototype. Like if you're doing a demo or prototype, by all means. Like throw something, you're at a game jam, right? Throw something together really fast and just like sprint. But you know, if you're building something that's meant to last for a long time, you really have to keep in mind that taking a little extra time to build it right could save you a lot more time and money in the long run. Another thing to keep in mind, this is really important. Adding features increases complexity exponentially, right? This is something that, you know, I kind of experienced in my transition from being a student to working professionally. You know, our projects as students, they were really pretty small. And even our team projects, right? Even the ones like we spent like a whole semester doing a team project, they're pretty small. And, you know, I would look at some of our projects and I'm like, wow, we did like 80% of, you know, the features of this, like, you know, professionally released game. But what happens is when you start adding these new features on, everything is interacting with everything else. And, you know, that's how complexity can really ramp up and grow exponentially with these larger code bases. Another tip for developers is, you know, knowing how to prioritize issues. You get, you know, the highest priority issues that you're ever going to have are issues that are preventing someone else from making progress with their work. Those are called blocking issues. Those are always important. Beneath that, I would actually put some critical things that I'm really uncomfortable with. You know, the things that carry the most risk, the things like, oh, I'm not sure how this is going to come together. If you're at the start of a project, you might be most tempted to take on the problems you're most familiar with, and you get like that nice little charge of reward, the feeling of reward for getting that thing done. But those aren't your highest risk things. Those are the things that you could maybe, you know, rush a little bit on towards the end of the milestone. Whereas the big scary things, you don't know how they're going to go, those are the things you typically want to tackle early on. So by risk, blocking issues. Okay, let's talk about growing as an engineer. Well, engineering takes practice. So writing code is the number one way of doing it. Evaluate your successes and failures. You know, there's a quote I love, good judgment comes from experience comes from bad judgment. So don't be afraid to use some bad judgment and do some learning. Get code reviews. Depending on where you work, you might not have a choice. But if you do, especially when you're starting out, get some code reviews, get some feedback from other people on your code. explore different approaches and philosophies. Sometimes I feel like, this can happen within a company, especially between companies. It's almost like political groups, right? Because like everyone is sort of like talking to each other, right? And there's sort of this sort of group opinion starts to form about certain things. So if you work at one company and then you go to another company, people's opinions on things can really shift quite a lot. So when I say explore different approaches and philosophies, I mean like step out of that comfort zone, step out of that group, step into another group and learn their ways too. You don't have to adopt the other group's beliefs. You just have to understand them. Because I think the richer and more varied understanding you can get, the better. I know from, I didn't go to grad school myself, but from people who do, a lot of people try to, do their postgraduate at a different place than they did undergraduate. And what they're trying to avoid, the term I've heard is intellectual incest, right? Basically, they want to have a variety of experiences in a variety of different thought communities. I think that's incredibly valuable as a software engineer as well. Talk to other software engineers. This is great if you're working, at a company in an office. Go to lunch, talk about work. You'll learn a lot talking to the other software engineers. Oh, okay. Yes. Good judgment. Yeah. So I already said this quote. It's a very good quote. Also, this one I do know is Miss Frizzle. Take chances, make mistakes, and get messy. And finally, one final thought to leave you with is always focus on the product. Code is a means to an end. As a programmer, this can be difficult because we can easily get sucked into just thinking about the code itself. But we should always remember that this is all in service of a product. That is not to say that the code should be bad, because bad code is going to be harder to maintain and buggier, and that's not going to be good for the product. But it is to say that all of our decisions should be motivated by what the end product is going to be. All right, so that's my talk. All right, so any questions? Yes.
So, as someone who's like, I'm in my sophomore year college right now, and I'm taking, computer science classes every semester, learning to code and such. I'm curious how, like, in your free time, for people who are like learning to code and like expanding their skill set, how do you I guess think of like something to code exactly? Because there's like so many, because like it's
make a
so many
game.
things you can do, but like also there's like not necessarily any like literal problems, because technology nowadays is so modern, and there's already like solutions everywhere.
That's true. There are solutions everywhere, and I think there's always a need for new solutions and new software. Ideas that I would suggest is first and foremost to pursue something that you're going to find interesting. In a lot of cases, that's going to be a game. If you're having trouble thinking of game ideas, join the Game Developers Club and get with the team. There'll be no shortage of ideas for things to build. But if you want to step outside of games, there's a lot there as well. You might find things in your own life, maybe there are hobbies you pursue or something where a certain kind of software could help that's not available. There's one story I remember. There was a pretty young guy who was really into sneakers. He was really into these sort of like high-end sneakers that people would buy and sell. And he wrote like a little app, I think at first mostly for himself, for like tracking the value of sneakers, as someone who was buying and selling sneakers. And then like he's, put the app on the App Store and made a lot of money off of it. So starting with, something and something you're passionate about. It could also even be something that, someone you're close with does a lot of. Maybe you have like a sibling or something who teaches music class, and They need, a piece of software for, keeping track of their students' progress, something like that. So I would say, that there's as much software as that's been written. There are always new things to find and just sort of explore the world around you, I would say. Okay, I see a lot. This one, maybe? Yep.
I have a question. When you were talking about assumptions, what did you mean by things that can't go wrong?
That can't go wrong. Assumptions are things that can't go wrong are assumptions that you hold so dearly that you think they couldn't possibly be assumptions. I think I might have saw that one first.
I think building on that for the assumptions, I wanted to comment just like I think that's a really good way of doing it. I think just this morning I was working on a project and basically a piece of data from one system passing to another, it didn't pass correctly, and I assumed the data itself was correct, and then it turned out that not to be the case, and I had like 30 minutes for a small little issue.
Yeah, that's software, baby. I think so. This one.
So considering that code does exactly what you ask it to, and that's both good and bad, what are the best ways to find what you don't think is an assumption, but turns out to actually have been an incorrect assumption, and that you just caught on to? Because like my previous coding project, there were two functions with the same name, and there was one function that wasn't working. And I looked at the function that I thought was being called with the same name. I was like, that should be correct. And I realized there's one in a different CPP file. I looked, and that one, I'd forgotten to write the if-else statement and even made a note for myself to write the if-else statement. I was like, oh.
Yeah, I mean, I would say if you're approaching a bug and something's happening and you can't imagine, why this thing would be happening, it would be to write out all the individual steps that the software is going through to guarantee the not bugged outcome that you're expecting. And when you write out all those individual steps, those individual steps that you might feel very confident in, those are the assumptions. And those are the things that you can go back and test. Okay, that's good to hear. And nowadays, I think it's, so one up there. Yes.
A problem, so I use test-driven development like 90% of the time because on the topic of assumptions, that's usually the go-to way for catching what went wrong. I have a problem that I hit frequently where I'm writing so many tests that it's taking forever to get the code done. So I'm like, okay, so you're going to skip these other tests. And then I hit bugs and they're all in the one where I didn't pass. If you had it.
Yeah, I mean, speaking of communities of thought, I've been in some very different communities of thought when it comes to testing. For most of my career, I was working at Firaxis or other places like Firaxis where they wrote no tests whatsoever. And then I came to Meta and they're like, oh, we're trying to get 90% code coverage with these tests. And of course, the tests are very time consuming to write. And in my very limited experience, now this is limited, and this is a bit of a hot take, I don't know that it really increased the stability of the software all that much. Now this is very limited experience. We're talking about just the projects I've been working on at Meta. I don't know if I thought that they were more stable for having had tests. Now people are using AI to generate the tests, and the AI-generated tests are usually pretty bad. So you could do that, but it might not be good. I do think, look, there are many, many software engineers out there who very strongly believe in test-driven development, and I am sure there is a lot of merit to it. But I also think, sometimes, or a lot of times, it's these sort of complex interactions between systems where the bugs lie. And, unit tests don't always cover that. That's not to say that, we shouldn't have automated testing or anything like that, but in my experience, it is a lot of effort to go through, and it doesn't, in my opinion, always rise to the level of helping enough that the investment makes sense.
There is like programs you should and should not do it with. It's not a for all
Yeah,
type of thing. I think it's good for like complex, more not data driven, but more like intuitive type of systems. Other things like if I'm in a scripting language, it's a mess.
yeah. I'm curious. Russell had his hand up. I think you might have some.
I'm curious where you would draw the line between assumptions and invariance.
Assumptions and invariance. Can you define what you mean by invariance here?
Okay, I mean, so I guess what I was getting at for some of the things here is, so we're talking about assumptions, and they tend to be the things that are assumed, things that you just kind of write and without really necessarily expecting to build into the system. But you can take those a step further, and at least, I don't know, I've called them this, I've seen them described this way in other things, is promoting those assumptions to invariance. Generally, this is done through self-documenting your code through like ensures and checks to be like,
Yeah.
this is a thing that should always be true. We're going to put in code that checks that all the time. Now, this is kind of like test-driven stuff. It's not, but it's not separate code. It's part of the system that you're building to be like, here is like I'm gonna document and say when this function gets called, this thing should not be null.
Mm-hmm.
And then if that assumption never breaks, your code is going to break immediately, and you can be like, why the hell is that happening? Why is my data coming through and it's wrong?
Yeah. I mean, this is a perfect example of why it's great to talk to other software engineers. I hadn't heard the term invariant used before. I just learned a new thing. Great to talk to other software engineers. But yeah, absolutely. I think that those kinds of verifications and checks are vital to making debugging easier, because when one of those fails, that really helps you point to where the problem is. So yeah, absolutely. I'd say it's a very helpful way of, I would more sort of describe that as checking assumptions. Yeah, absolutely. And I think that yeah, there's tremendous value in that, and probably something I should add it to that slide.
Like the nasty thing about assumptions is that they're, as with most things, assuming they're generally unspoken.
Yeah.
And so,
Yeah.
and especially even when you're having conversations with other engineers in your team or other people on your team, that group think of like all thinking at the same thing. And so when somebody new joins the group and they start asking some of these like weird questions that are maybe just like, oh yeah, why are we doing it that way? That by having a thing, by writing down that assumption, it's now kind of become a different thing.
Yeah.
That makes it no longer unspoken. You've got some code, and somebody is going to go into that code and go, why do we have this? Why is that wrong all the time? And you can talk about it.
Yeah. Okay, I think that's brilliant. For the sake of the recording, Russell was saying that when you check a certain assumption in the code by like adding an assert or something, you're formalizing it. Whereas, assumptions can be unspoken. And I think that's a great way of putting it. I think that's probably a good thing to add to that slide. All right, next question? Oh, sorry, one more. Okay, this is the last one. Yep.
So I've had a lot of times sometimes saying that, oh, do we have enough people, or sometimes like recruit too many people and it's hard to give them all like roles to do. When you get like that, like what signs do you usually have that like either you need more programmers or you have too many, and how would you kind of deal with that?
I think generally fewer programmers is better. Because the more programmers you get on your team, the harder it gets. I think that when you know you don't have enough is probably when you get to the point where it's completely unrealistic to meet your goals in the timeline you have with the number of engineers you have. I think another reason why you might want to pull in another programmer is if they have a particular kind of expertise that you're missing on the team. You know, maybe you need a multiplayer program or something like that. And that's really going to accelerate you to have someone with that kind of expertise. But I would say, given those two constraints, past that, I would say that we want to be as minimal as possible with the number of engineers on the team, because as the number of engineers grows, the overhead for communication and the amount of missing context increases. There's this famous book on software engineering, which was written a very long time ago, but a lot of its lessons still hold, called the Mythical Man Month. And it's basically saying, they're talking about how a lot of times a company will throw a bunch of engineers on a project right towards the end to try to accelerate it, and it doesn't necessarily work very well. And there's a great quote from that. Just because one woman can make a baby in 9 months does not mean that 9 women can make a baby in 1 month. So it's important to keep in mind. And they do go into a lot of great detail in that book about how the bigger your team grows, the more overhead you have for things like communication and everything like that. Okay, so I think that's all for my time today.